You can start punching in your attendance now. You're able to see the screen?
Yes, sir.
Okay, good.
Yes.
Yeah, all right. Okay, fine then. Today, let us go ahead with biased positive clamper. All right. So, what I will do, I will not do unbiased clamper, because unbiased clamper analysis is going to be a lot easier compared to biased clamper, right? So, first, let me do biased clamper, and you guys can try out with unbiased clamper. Okay, fine. Yeah, good to go, right? Fine. Biased positive clamper. Okay, so this biased positive clamper works on the complementary logic. Okay, in the sense, what you have to do is you have to just invert the diode connection. That's all. If you invert the diode connection, what you get is a positive clamper. Okay, so first let us look at the circuit. Okay. Now, a positive clamper, in case of positive clamper, okay, what happens is that the capacitor gets charged during the very first negative half cycle of the input. Right? So that's the complement of, you could say that, negative clamper. Okay, so in negative clamper, capacitor gets charged for the first positive half cycle. In case of positive clamper, the capacitor is going to get charged for the very first negative half cycle. All right. Okay, so that being said, I can go ahead with the circuit diagram. So this is your capacitor. Okay, this is your diode. So what I'm going to do in case of positive clamper is that I'm going to invert the diode terminals. All right, and let me provide, let's say, the reference source. Okay, I'll put the reference source in this direction. Okay, let's say this is VR, and let's say this is made up of silicon diode. All right. And this is your source. Let's consider a sinusoidal source. Load resistor. It's your capacitor. All right. So let us define certain things. Let us take the time constant of the circuit tau as product of RL into C is equal to very high, right? So this is what is required for a successful clamper operation. Okay, right. So now let us look at the charging cycle. Pretty easy to understand the charging cycle, okay, or identify the charging cycle. What you have to do is you have to identify the half cycle which is going to forward bias the diode. Okay, so if the diode gets forward biased, the capacitor is going to get charged. Okay, so the diode gets forward biased in this direction, isn't it? In the anti-clockwise direction. Now, in order to have the current flow in the anti-clockwise direction, you must consider the negative half cycle of the input. Okay, fine. And let us also mark the polarity for the capacitor. So, okay, say terminal A of the capacitor is connected to negative terminal of the source. Hence, terminal A attains negative polarity and the opposite plate attains positive polarity. All right. And let's consider the voltage across the capacitor as VC. Okay. And also, let us consider the barrier potential of the diode. Okay. So, barrier potential of the diode, okay, going to be something like this. Upper side, you will have a negative terminal, and on the lower side, you will have a positive terminal. Okay. This is Vk. Okay. So, Vk represents the barrier potential. I'll write Vk is equal to barrier potential. Okay. Now, if you observe the connection sequence of Vk and Vr, you see that both Vk and Vr are trying to send the current in the same direction. Okay. So, in the next observation, probably you can write net DC potential, okay, is equal to Vk plus Vr. All right. So for the charging cycle, what we will do is we will redraw the circuit, okay, by substituting diode's equivalent model. All right. And this is your diode. Since you are substituting the diode model, so let's consider this diode as the ideal diode. Okay. And let us also place the reference source as well as the barrier potential. Okay. So the total potential is Vk plus Vr. So let's write Vk plus Vr as the total potential. Okay, the negative half cycle, let me write. Okay, and the maximum value of the sinusoidal input is Vm. This is your Rn. All right, fine. This is V0 minus plus. Okay, minus plus. So in the negative half cycle, so in the very first negative half cycle of the input, capacitor gets charged. Okay, so let's mention the polarity as Vc. Okay, once the capacitor is charged, okay, you can also observe that to charge the capacitor, D should be in on state. Should be in on state. Okay, because it needs a closed path for the charging to take place. Okay, so what I'll do, I'll just close the diode terminals. Okay. Okay. Next, apply KVL in anti-clockwise direction, ACW. Okay, ACW stands for anti-clockwise direction. So when you apply KVL, what do you get? Minus to plus Vi, then plus to minus. So that's Vk plus Vr, right? So in order to, instead of writing two terms, what we can do is we can take Vk plus Vr as Vt. Okay, total threshold voltage we will take. All right, so that's minus Vt. Okay, and minus Vc is equal to 0. Okay, minus to plus Vi, and plus to minus Vt, plus to minus Vc is equal to 0, or voltage across the capacitor Vc is Vi minus Vt. Okay, so this is capacitor voltage. Capacitor voltage. Fine. Once you are done with the finding out the value for the capacitor voltage, you can proceed to finding out the output. Okay, so next you can write output cycle. Okay, you know the usual procedure, right, to find out the output. So what are you going to do? In order to find a cycle of output, what you consider is a positive half cycle of the input and a negative half cycle of the input. So first let me consider positive half cycle of the input. Okay, so fine, let me consider the positive half cycle of the input. Quickly let me draw this circuit. So polarity is reversed, because we are dealing with positive half cycle, right? But the capacitor polarity are not supposed to change, because the capacitor circuit is having very high time constant. Okay. So as you can clearly observe in the circuit that both VI and VT, they are trying to circulate the current in the same direction. So as VC. Okay. So VI is trying to circulate the current in clockwise. VC is also trying to circulate the current in clockwise direction, and VT as well. Okay. So thereby, reverse biasing the diode D. Okay. So diode gets reverse biased. Okay. See, again and again, I'm repeating this. If at all you have understood the clamper logic, you don't have to write again and again that diode is reverse biased. Okay, you can always open the diode terminals, because whenever you find the output of the clamper, the diode will be in reverse biasing mode. Okay, whatever may be the circumstance. So diode gets reverse biased. Let's open up the diode terminals. Okay, and let us also mark the output polarity. Okay, fine. So let's apply KVL now in clockwise direction, because we are dealing with positive half cycle. So apply KVL in clockwise direction. Okay. So what do you get? Minus to plus, then minus to plus. Okay, and plus to minus, we know is equal to 0. Okay, or output V0 is equal to VI plus VC. VI plus VC. Okay, so this is your output equation for positive half cycle. Okay, so that means to say, let me write it here. When, so say this is equation star. Okay, so from star. Okay, so when your input is 0, okay, what is the value of output? Output is equal to VC. And what's the value of VC? You have already found. VC is VI minus VT. Okay, yeah, one small thing I forgot, that when your input attains maximum voltage, okay, your capacitor will have a voltage which is equal to Vm minus Vt. Okay, this is what I should have written in the beginning. All right, nevertheless, so Vc is equal to Vm minus Vt. So your output V0 is Vm minus Vt. Okay. On the other hand, when your input rises to positive maximum, your output will have a value which is equal to Vi, right? What is Vi? When your input rises to positive maximum, it is Vm. So Vm plus Vc. So Vc we know, Vm minus Vt. So output peak, the output peak going to be at 2Vm minus Vt level. Okay, 2 Vm minus Vt 11. I'll just mark it with a different color, okay, because this will help you in sketching the waveform as well. Okay. So, you know, this blue boxes you would be requiring while plotting the output. Okay, so that's for the positive half cycle. So you can clearly observe that your input had its initial value at 0 volt level. Okay. On the other hand, you can clearly observe here. Okay. Please follow the pointer. When your input is at 0 volt level, your output is at some positive voltage, right? And what is that positive voltage? It is Vm minus Vt. Similarly, when your input is at its maximum value Vm, the output positive peak is being pushed to a different level, which is 2 Vm. So basically, what is happening in case of positive clamper is that your the wave is getting shifted in the upward direction. Okay, and that sense, we call it as positive clamper. Okay, let's see what happens to the negative half cycle. Okay, so let's consider negative half cycle. So in the negative half cycle, what you have to do is you have to inverse the polarity. Okay, polarity of the input. Minus plus is the capacitor voltage. Source with the reversed polarity. Okay, and this is your diode. It's the threshold voltage, which is DC in nature. Minus plus V total diode. Okay, and this is your output. Okay. So you can see in case of negative half cycle is that Vc and Vt, they are trying to circulate the current in clockwise direction, right? Clockwise direction. On the other hand, the input source Vi is trying to circulate the current in anti-clockwise direction. Okay. Nevertheless, the diode will be in off position. Okay, so I can write the condition something like this. Okay, if Vi is less than or equal to Vc plus Vt. Okay, why Vc plus Vt? Because Vc and Vt is having the same polarity, right? I mean, they are kind of additive in nature. Hence, I'm taking the total voltage as Vc plus Vt. Okay, so at the maximum, your right hand side can be equal to left hand side. Okay, or your right hand side can be less than your input. Okay, as long as your input is less than or equal to Vc plus Vt, diode D is in off position. Off position. Okay, so you can open up the diode terminals. Okay, and you can apply the KVL. Okay, in the anti-clockwise direction. Apply KVL in anti-clockwise direction. So what do you get? Vi plus V0 minus Vc is equal to 0. That implies V0 is equal to minus Vi plus Vc. Am I audible?
Yes, sir.
Yes,
Yeah.
sir.
Fine, fine. No, just wanted to see whether you're sleeping or not. Fine. V0 is equal to minus Vi plus Vc. Okay. So when your input is equal to 0, okay, output as expected will be at Vc level. And what is Vc? Vc is Vm minus Vt. I guess, yeah, Vm minus Vt. All right. On the other hand, when your input hits the negative peak value, Vm, your output will be at minus Vm plus Vc or minus Vm. Okay, Vc expression already I have written in the above line. So it is going to be minus Vm plus V2. So Vm gets cancelled. So your output going to be at Vt level. Vt level. Okay. So
Sir,
this, yeah, tell me.
minus Vt level.
Minus Vt, yeah. Okay. See, minus Vm plus Vc. Yeah.
Yes, sir.
Minus Vm plus Vc. And what is Vc? Vc is Vm minus Vt, no? Yeah, you're correct. No, this should have been minus, no?
Sir, you have cancelled minus VM and minus VM.
1 minute. 1 minute. Yeah. Roll back. Yeah. So minus Vm, that's the input value, right? Then plus Vc I should write. What is Vc? Vm minus Vt. Yeah, this is what I was supposed to write, no? Minus Vm plus Vm gets cancelled. So V naught is equal to minus V2. This is correct, right? Can you confirm?
Yes, sir. Yes,
Yeah.
sir.
Okay, fine. So we are done with the positive half cycle analysis as well as negative half cycle analysis. Okay. Now we can plot the waveforms. Okay. So it is expected that your output is shifted in the upward direction. Let's see what is happening with the output. Let me just draw the axis. So this is your input. All right. Let's first sketch the input. Okay, so that's your input, Vi, the time axis, 0 plus Vm and minus Vm. Okay, fine. Now let us sketch the output. Can anyone tell me what will be the value of the output when the input signal value was 0? So when Vi is equal to 0, output is Vm minus Vt, right? So let's say this is the 0 reference of output. So when your input is 0, output is Vm minus Vt. So some positive voltage. Okay. So let's say this is the value. Okay. So let us write this value as Vm minus Vt. Okay. On the other hand, when your input rises to Vm level, output will be at what level? In the positive half cycle, when your input rises to Vm, your output peak will be at 2 Vm minus Vt level. Okay. So that is somewhere here. 2 Vm minus Vt level. And once again, when your input falls to 0, the output will be at minus Vm minus Vt level. Okay. Okay. So that's your positive half cycle of the output. Once again, in the negative half cycle, when your negative half cycle starts from 0 volt level, output will be at minus Vm minus Vt level. And when your input achieves the negative maximum, okay, the output peak will be at minus Vt level, So somewhere here. And once again, when your input reaches 0 volt level, the output value will be at minus Vm minus Vt level. Okay. Fine. So this is your output waveform for a positive clamper. Okay. So now let me just draw the axis. Okay, let me use the white color. This is your axis. All right. Now you can clearly observe that your waveform is getting shifted in which direction? Upward direction or downward direction? Upward direction, right? Your wave input was at 0 volt level. Okay, now the origin of the output waveform being shifted to a new level, and that level is Vm minus Vt. Okay, so this is the shift. Okay, so this is the DC shift. You can say positive DC shift, hence a positive clamper. Hence a positive clamper. Okay, now, yeah, I have to write this peak value also. This is at minus Vt level. Okay, so VPP, that is V peak to peak, it should be 2 times the maximum value. Let's check whether we are getting V peak to peak as 2 times the maximum value. So what is V peak to peak? The positive peak, that is 2 Vm minus Vt, okay, minus negative peak. So minus of minus Vt. Okay. So minus of minus Vt is plus Vt. So plus Vt minus Vt is going to get cancelled, and VPP is equal to 2 Vm. Okay. So once again, I repeat, in case of clamper, the appearance of the wave is not changed. Okay. Your input was a purely sinusoidal wave, and the wave shape of output is also sinusoidal. Only the difference is that the origin is being shifted. Okay, so in this case, the origin is shifted towards the positive direction. Okay, so that's your waveform, and you can quickly draw the transfer characteristics as well. Transfer characteristics. Okay. V naught, Vi minus Vi minus V naught. Okay. So during positive half cycle, when your input is at 0 volt level, your output will be at Vm minus Vt level. Okay, Vm minus Vt level. Let's say somewhere here. Okay, Vm minus Vt. On the other hand, when your input reaches plus Vm level, your output will be at 2 Vm minus Vt level, right? So 2 Vm minus Vt level, somewhere here we can show. Okay. So this is Vm minus Vt level, and 2 Vm minus Vt level, I will show somewhere here. Okay. On the other hand, when your input becomes minus Vm in the negative direction, okay, what will be the output value? When your input becomes minus Vm, output is minus Vt. So this is your minus Vt, right? Because minus Vt should be plotted in the downward direction. So minus Vt. So somewhere here. Okay. And then you can just join the lines. This line and or this as well. Somewhere here you can join. Somewhere here you can join. Okay. So that's your transfer characteristics. Okay. That's your transfer characteristics. Okay. So that concludes Clamper chapter. Okay. So what I will do tomorrow, I'll start with transistor basics. Okay. Transistor biasings. I'm going to start. Okay. Do you have any doubts in today's?
No, sir.
No. Okay. Fine. So soon after this class, I will circulate 2 quizzes. Okay. No, 1 quiz. One I have already circulated, which is based on biased negative clamper. So today I'm going to circulate biased positive clamper. Okay. By tomorrow morning, you are supposed to complete it. Okay. Any doubts? If you have any doubts, you can just let me know. Okay. One question on today's topic. What will be the, you have to just type in, okay, you have to just type in the answers. Consider ideal diode for the same circuit. Okay, you just assume that ideal diode is present. If you consider ideal diode, what will be the positive peak and the negative peak of the output waveform? Just type your answers in the chat box. Considering the ideal diode, what will be the positive peak of the output waveform as well as the negative peak of the output waveform? Type in your answers.